So when we study autonomous equation, we use phase line to analyze the solution. A lot of time for autonomous equation, you might have a parameter involving your equation. For example, the population model we studied before, and here k is a parameter for different species. This k value will be different, and we want to see how the solution changed by the different value of k. And we use this example's next example to introduce the bifurcation analysis. For bifurcation analysis and for this equation, and we have a parameter mu, and which is for this equation, if mu equal to 0, and this is corresponding to dy dt equal to y squared minus 2y. For this example, given this particular mu, and we can study the equilibrium point, and we can classify the equilibrium point. Do the phase line study. Draw the phase line. And for this one, and because we set the f here, we call the f mu y, mu is subindex for the parameter. And given mu equal to 0, we have y squared minus 2y, and which know is 0 and 2 are the equilibrium points. And now we can draw the phase line. On the phase line, the vertical line has 2 equilibrium points. And when y is bigger than 2, pointing up, and between 0 to pointing down, and when 0 less than 0, it's going to positive again, so it's pointing up. Look at this phase line. Near the point 0, 2, there's arrow and pointing and away from it. So we know this is tell us y equal to 0 is a source. Around the equilibrium point 0, and those arrow is pointing towards to it. So this tell us that we can tell this is a sink. If you use the theory how to take the partial derivative of y respect to y, you can also classify the equilibrium point. For example, at df dy equal to 2y minus 2. At y equal to 2, f prime equal to 2 is positive, so it's a sink. When f prime at y equal to 0 is negative, so it's a sink. That is for when we have a particular mu equal to 0. What happens when mu equal to 1? So when mu equal to 1, the differential equation becomes dy dt equal to y squared minus 2y plus 1. And this is a perfect square, y minus 1 squared. For this particular mu, and we solve the equilibrium, and that will give us, since it's a perfect square, and y equal to 1 is the only equilibrium point. This equilibrium point is actually repeated. So that's when we check the sign, and we know and y is bigger than 1 is pointing up, and because repeated, and below also the same sign. So this is a node. From these two scenarios, you probably see that the phase line or number of equilibrium change dramatically change for different mu value. And now, if we systematically to study this, and we'll see, and we're gonna do for a general mu and draw the phase line. So in other words, we're going to find the equilibrium and try to identify the direction and classify the equilibrium point if there are. So when we find the equilibrium for this general mu value, we have a quadratic equation. For a quadratic equation, and we can use the quadratic formula to find the roots. And so how many roots is depend on this discriminant. So the discriminant here is 4 minus 4 mu. It's really the 4 and multiplied by 1 minus mu. So giving this general formula, and we know when the discriminant is positive, then we'll have 2 roots. When the discriminant equal to 0, which is the mu equal to 1, and then we'll have 1 repeated real roots. when the discriminant is negative, and which is 1 minus mu less than 0, and will have complex roots. They are imaginary number, but there's no real roots. So in other words, when we're solving this differential equation, we are expect the y is in the real space, and there's no equilibrium solution when mu 1 minus mu less than 0. When mu equal to 1, the equilibrium is equal to 1, the previous we will look at. And when mu equal to 1, and that's the case we have checked, we have one equilibrium, and this equilibrium equal to 1, it's a node. And when mu, and here look at this discriminant, and which is less than 1, and will have 2 roots. So when the discriminant is positive, mu less than 1, we have 2 equilibrium. One is the source, one is the sink. When the discriminant is less than 0, when 1 minus mu is less than 0, which is tell us mu bigger than 1, and then we have no equilibrium, the phase line is really trivial. It is always positive, pointing up. So if we systematically putting this how solution change regarding to mu, and this is the bifurcation analysis. And first we're going to see this graph, which is bifurcation diagram. And on this graph, on a bifurcation diagram, and we want to construct the coordinates, which is the horizontal is the parameter mu, and the vertical is y. And then we're going to draw all the possible scenario for the equilibrium. For example, here, and we have mu equal to 1, all you have those two. Actually, one of them will be good presentation, represent the scenario. So here you can draw at mu equal to 0, or you can draw mu some other value. And beside those coordinates, and we draw sample phase line for different mu value. And one important thing is, beside draw those sample phase line, and we want to draw the curve, and this curve is all the possible equilibrium point. You might wonder where this curve comes from. And if you remember, we are solving this quadratic equation. And that quadratic equation, y squared minus 2y plus mu equal to 0. And those are the curve, and if we have a possible mu value, where the equilibrium points are. Okay? So from this diagram, you probably see that giving and those value and the number of equilibrium change dramatically from 2 equilibrium at mu equal to 1, we have 1 equilibrium, and then become 0 equilibrium. And for this particular example, the bifurcation happened at the number of equilibrium change. So when the number of equilibrium change, and that particular value of the parameter is called bifurcation value. There are other scenarios. You might have the same number of equilibrium, but the property, the type of equilibrium can change. For example, from change to sink to other type. And those value, when either the number of equilibrium change, or the property of equilibrium change dramatically, is the value called bifurcation value. Bifurcation value is talking about the value of a parameter, and it's really concerned the number or the type of equilibrium. So giving a differential equation has one parameter, and we'll construct a coordinate, and which shows horizontal is a parameter and vertical is 1. And then we'll try to find all the possible equilibrium. And for example, this example, and the equilibrium is when we have all those points, the real possible y value for different mu value. And then you draw a few sample phase line, and this one is needed because this one shows the scenario when we have only one equilibrium. Phase line need the direction. And another one when mu is less than 1, and which is positive down, up. Another one when mu is present, there's no equilibrium. So this is a brief bifurcation diagram. So next we're going to work on example.